In this lecture, I'm going to describe uh, how to understand the gravity fields versus the gravity force in pi space, and how those two relate to one another. In the example diagram I've shown you here, this is the traditional Einstein view of a gravity field. It shows the path that an object will follow as it falls into a gravity field, and one can see that in the space-time diagram, the mass, the path that the mass follows is in towards this central point at the bottom here. Um, in the Newtonian view of the world, we're given this formula here, which is the force of gravity is g times m1 m2 over r squared. So let's try and kind of bring those two ideas together pretty simply. If we try to understand the formula for gravity, the force of gravity, there's two aspects to it. Force in the Newtonian world is mass times acceleration. Now the mass in this example here is mass m2, and the acceleration is formed by the large G, which is the universal gravitational constant, times mass m1 of the planet, and divided by the radius r squared, and that is the distance that the mass the object is from the center of gravity. So for a planet, we can then say that the force of the gravitational constant on the planet, if it has a radius r, is g times m1 over r squared. Now that's pretty straightforward. You can see that the acceleration component is generated by g times m1 over r squared, and then the mass component is m2. But then if you think of this diagram here, um, where you see this gravity field, how does that gravity field relate to this formula here? Okay, so let's just break it down. So in pi space, the way we understand gravity is reasonably straightforward. A gravity field is generated by the mass of the object. So g times m1 over r squared generates a per atom area change in in a gravity field. So put very simply, if you're inside a gravity field, um, and you move up within a gravity field, your pi shell or atom gets larger. If you move down in a gravity field, your pi shell or atom gets smaller. So if we take a look at this diagram again, you can imagine as you move down towards the central point of the center of gravity here, that the object, the pi shell atom is getting smaller. It's being compressed. As you move up, it gets larger. Now the nice thing about the Newtonian formula is it gives you units of measurement. So you've got units of measurement in relation to distance and units of measurement in relation to time. Now, when a pi shell gets larger, its area gets larger. So the gravitational constant can be seen simply as a rate of area change with respect to distance or time t squared. So as you're moving up, it gets larger, and as you're moving down, it gets smaller by this gm1 over r squared ratio. So a stronger gravity field essentially just means that when you move down, you lose area with respect to an observer at a faster rate. Now that's okay and that's fine, and we can understand gravity in that respect. But there's something really very kind of subtle in this understanding that is important to describe, and that is that let's take an example of gravity on the ground. Let's take the example of you outstretch your hand and you have two objects in your hand, and one is a large metal ball, and the other is a smaller metal ball, like a ball bearing. Now, if you stretch out your hand under gravity, the hand that has the larger metal ball, you will require more muscle strength to keep that object up. So let's say you take an object and you try to lift it under gravity. The mass of the object is important. Uh, it's very important. In other words, if you try to lift a very heavy object and you try to lift a very light object, there's less work involved in lifting a heavy object versus lifting a light object. Okay. Now the way that the way that Newton described this was he said that the force to move something is a product of the mass of the object times the acceleration. Now, if you look at the example that I've given you here of a gravity field, I didn't really include the the mass component. I just said that as an object moves up, it gets smaller, gets larger by a certain amount, and as it moves down, it gets smaller by a certain amount. I didn't bring into that discussion the mass at all, and this is a very important point, and I have underlined this here in the document. This document is called More on Gravity, and it's on the website pispacetheory.storytwig.com. But the really important thing about a field is, and this is a very very subtle point, and it's not really called out in either the it's not really called out in the Newtonian work. It's kind of explicitly stated in the Einstein work. And what the Einstein work essentially says is that in the diagram is that all that a gravity field is doing is altering the geometry of objects, right? And that's essentially what this diagram is trying to kind of explain, that it's all about geometry being altered. And it's the question is the geometry of what, and of course the answer is the geometry of atoms, or what I would call pi shells, which can be just a larger group of atoms. So, but if you're on the surface of a planet and you try to lift two objects, one heavier than another, like a small ball bearing and a large metal ball bearing, or a large metal ball, it's very difficult to keep the heavier object up because you need a certain amount of muscle strength, right? So these are two examples, and they're actually, you in the Newtonian work you can think of these in some ways as the same thing, but they're not, and this is what I'm trying to describe in this lecture. So basically, in the first case, right, we uh, we have where you have the two objects in either hand. What you have is your hand is comprised of atoms, and the object you're holding is comprised of atoms. So what you have is atoms applying a force on other atoms in a gravity field. Okay, that's the first case. So if you think of yourself holding something, you could grab anything you want under gravity and you hold it out. You will need a certain amount of muscle force. Eventually, your arms will tire under gravity, right? But the point is, it's atoms interacting against atoms. So what you have is the Newtonian view of it, which is force is equal to ma. So you have one force opposing another force, and the two forces balancing each other out according to the Newtonian laws under gravity. So that's case number one, right? Now case number two is a more subtle case, and it's not tremendously obvious to people who use their intuition and don't know gravity well. And the second case is, let's say you take those two objects, right, and those two metal balls, one large and one small, and you you basically drop them under gravity, right? Now, although it took more work to hold the heavier ball, when you drop the two of them under gravity, what happens is they both fall at the same rate. Okay, and that's the tell. The tell is that the gravity field is not applying a traditional Newtonian force on it, in the sense that the gravity field of the object is not doing force is equal to mass times acceleration on that object. All that the field is doing is altering the geometry of the object that's falling, right? Now, the two masses do interact. So the mass of the Earth will interact with the mass of of the ball that's falling, and if it's a large enough mass, the center of gravity orbit will change. But in terms of actually the rate at which the heavy ball and the smaller ball fall, they both fall at the same rate in a gravity field. So this is a diagram trying to explain that principle. So although you might be inclined to think they're the same thing, holding something under gravity and feeling a force and pushing against it, and dropping something under gravity and measuring the amount of force that that object has when it hits the ground, they're not the same thing. And this is essentially what the Einstein work sort of shows us, that when you fall under gravity, right, what the what the what the is happening to the atoms in either the heavy object or the lighter object, it's the same effect on both objects. It's independent of the mass, the rate at which it falls in a gravity field for small objects. It's the same speed. Yeah, and and it's counterintuitive, right? And the reason that it happens is because all that the gravity field is doing is altering the geometry. In other words, when it goes down, it gets smaller by a certain area change. Now, this is the pi space theory view of it. It's losing area as it moves down by a fixed amount, and both objects, no matter their size, both of them lose the area at the same rate. Yeah, and that is why they both fall at the same speed. But if on this case over here, if you hold those two objects in your hand, you can feel there's more work required to keep the heavier object up than the lighter object, and that is where you have two objects working against each other, two atoms working against each other. So that would be seen as force is mass of object 1, acceleration 1 again equals mass of object 2, acceleration 2, and those two equalize out. Okay, that's the Newtonian equal and opposite reaction idea in the Newtonian laws. But in this case here, in the second case, what you have is you have an object free falling under gravity, right? And what you find is that it's a atom interacting with the field, right? So if you want to try and understand the Einstein work better in through pi space, that's essentially the idea. It's an atom interacting with a field versus an atom interacting with an atom, and the key take out of this is that the field ignores the mass of the object when it falls under it. It ignores it. The two masses do have a bearing on each other in terms of orbits, in terms of orbital positions. But if you have a tiny object like a ball bearing on the planet Earth, it makes no difference to it. But the point is the field that you're inside is just altering your geometry, and that's what I say at the very end. To sum up, a field just alters the geometry of a pi stellar atom. And the most important thing to take out of this is that that is essentially what a magnetic field is also doing. Fields alter geometry, alright? They alter the geometry of objects, and the key thing is they're powerful because they ignore the mass inside the object. Whereas if you try to get one object to push against another object, the two objects, you do have to take into consideration the mass in each object. But in a field, in the case of a field such as like in a cyclotron, where you're using a magnetic field to accelerate something, it will just compress and compress and compress and compress an object. It won't take into account the mass. And we see that when you drop an object under gravity, and the heavy object and the light object, they both fall at the same rate.